Welcome to Further Dynamics Part 1, which is looking at using some calculus with Newton's laws. Before we start, I just want to revise a couple of key ideas. If you have force equal to a function which varies with time, then mass times acceleration is equal to a function which varies with time. Now, because acceleration is dv by dt, then you end up with m dv by dt is a function that varies with time. So mv is the integral of the function with respect to time plus whatever constant. Now that's the idea of impulse. Okay, the integral of a force, or the area of a force-time graph, is equal to the momentum, or the change in momentum. So you may recognize that from before. Now, if you look at another key point, if you have that force is equal to another function, this time g, which varies with x, then mass times acceleration is equal to a function which varies with x. So, from the rules that we used before, earlier on in the course, we can set acceleration as the differential with respect to x of half v squared, and so that is equal to v dv. So acceleration is mv dv by dx, which is equal to this function g that we talked about. So half mv squared, okay, where this is half of v squared, is equal to the integral of the function g with respect to x plus whatever constant. Now, you may notice, or you may have noticed already, this is equal to kinetic energy, and kinetic energy is equal to the integral of the force with respect to x. Or in plain simple terms, if it was a constant force, work done is equal to force times by distance. But this is the proper way to do it, rather than the simplification. So, that gives us two basic ideas. When the applied force is a function of time, A is equal to dv by dt. When the force varies with displacement, then we use acceleration is something else. Okay. Now, I'd like to use some of those ideas to go through a basic example before moving on to something a little bit harder in the next video. So this example is a question taken from exercise 3A from the Heinemann Edexcel textbook. And we're going to look at a particle, P, mass 0.2 kilograms, moving on the x-axis, and if we take the distance from the origin to P as being the distance x, the force acting on it is equal to 2 cos t, and initially the particle is at rest. So we're gonna go through the first few bits. The first part of the question is calculate the speed of p when t is equal to 2. Sorry, initially it's at rest at point O. So, from forces mass times acceleration, 2 cos t is equal to 0.2 a. Here's the force, here's the mass, here's the acceleration. So rearranging that, acceleration is dv by dt, and so we can work with this, and we now have that v is the integral of cos t dt, and multiplied by this constant, which works out to be 10. So when we try and find out the constant, We integrate cos t obviously, and that gives us sine t. And the constant c is found using the initial conditions, so when time is equal to 0, the velocity is equal to 0, and so in this case the constant is also equal to 0. Happy days. So the velocity is equal to 10 sine t. So the first part of the question is almost done, and you just have to set the conditions in. So the question asks, find the speed of p when t is equal to 2. So when t is equal to 2, the velocity 10 sine 2, and that gives us 9.092 meters per second. Second part of the question, part B, it asks for the speed when t is equal to 3. Well, this is a very easy step, seeing as we've already got an expression for the velocity, so we just put our new time in. 10 sine 3 gives us 1.41 meters per second. Now, the next part of the question says find the time when p first comes to instantaneous rest. So it's at rest when its velocity is equal to 0. So set velocity equal to 0 and then solve for a velocity. So you find sine t is equal to 0. What values will t give us 0? So we've got 0, pi, and any multiple of pi. So sin to the minus 1 of 0 obviously is what's given us t, and then we've got pi repeats. So p is first at rest, obviously initially, and then when time is equal to pi. Okay. Next part of the question. The question says find or calculate the distance OP when t is equal to 2. So the distance, well, we've got to velocity, but we didn't quite get as far as distance. So as velocity is dx by dt, all we need to do is integrate the velocity with respect to time, and we'll get the displacement of the distance. So in this case, x is equal to 10 integral of sine t with respect to t, and that gives us minus 10 cos t plus k. So we do need to find this constant k. We can set the initial conditions that were given in the question, where initially time is equal to 0, the particle is at the origin, so the displacement is 0. So 0 is equal to minus 10, where cos of t equals 1, minus 10 plus k, and k in this case is equal to 10. Okay, so just move the minus 10 to the other side. K is equal to 10. So we've now got an expression for the displacement, and we work with that. We have that the displacement is equal to minus 10 cos of t plus 10. So the question asked, find the distance OP when time is equal to 2 times 2. Here's the displacement, or the distance. Here's the answer. Job done. Okay, and the next question, the final question. Find the distance OP when p first comes to instantaneous rest. Well, we've already found out what the time is when it comes to instantaneous rest, so we use that time where t is equal to pi. We set x is equal to minus 10 cos of pi plus 10, and that gives us 10 plus 10, which is 20. Okay, so p comes to rest when OP is 20. So if I go back to the original diagram, okay, you may be wondering who drew this diagram. It wasn't actually Picasso, it was me. So we have that the particle p must oscillate in between this point O and a distance 20 meters away. Okay, so it's just a oscillator. Okay, I hope you've found that relatively understandable, and if you're struggling with any little bits, just have a look at the videos again. Okay, thank you very much.